Hello everyone. Uh, in the previous lectures, we have been discussing about homomorphisms of groups and one very important class of examples of groups, namely this dihedral groups, right? So this forms an infinite class of examples of non-abelian groups as this integer n ranges over uh, the integers from 3 up to all from ranges over all the positive integers greater or equal to 3. Okay. Yeah, and there are certain results around that we have been discussing. This is were obtained principally as an application of the division algorithm that we discussed long back, and part of this is at least we have seen certain instances of this proposition earlier also, right? At least in the context of this group Z, we have classified all the subgroups of Z, right? And we knew that they're all cyclic, and this proposition says that the statement that the subgroups of Z are all cyclic holds in greater generality, and the statement is that a subgroup of a cyclic group is cyclic. Okay, great. Uh, we have been discussing this notion of homomorphisms and so on. Uh, yeah, we have also discussed an important subgroup of this group OUT G. Okay, so this is called this group of inner automorphisms, and yeah, this were left as an exercise to you. Okay, anyway, uh, yeah, so let's try to discuss a bit about this notion of homomorphisms and isomorphisms. So suppose we start with two groups G and G prime, and we pick an isomorphism phi from G to G prime. Okay, I mean we are assuming that such an isomorphism exists, and then there are certain properties that holds as a consequence. Okay, one of the well-known property in this situation is, I mean, in this context is that for any element G inside G, the order of this element G is equal to the order of the element phi G. Let me read it once again. For any element G in G, the order of this element G. Okay, so I mean, this order of this element G is equal to the order of phi G. So there are two phrases that there are orders of two elements that we are interested in here. So one is this order of the element little g, which is an element of this group G. Okay, so the order has to be order of little g has to be computed here. So this is the least positive integer n such that g power n becomes identity. Okay, uh, I mean, and in the unavailability of any positive integer n, we set it to be 1. We set it to be infinity, right? Yeah, so this is something that you have to compute, or you have to, I mean, to understand the order of G, we need to care about the group G. Okay, and then to understand the order of the element phi G, we need to care about the group G prime. Okay, so this order is computed with respect to the composition law of G, and this order, the order of phi G, is computed with respect to the composition law of G prime. So we need to be at least a bit carefully here. Okay, so by now I think we have learned some of the subtleties of these notions. So yeah, but it's good to revisit. Okay, yeah, and it says that for any positive integer d, I mean, as a consequence, one can deduce that for any positive integer d, the number of elements of G of order d is equal to the number of elements of G prime of order d. Okay, yeah, I mean, as you can imagine, once you have this first part, then the second part shouldn't be too difficult. Okay, should follow as a quote unquote natural consequence. Anyway, so let me just introduce fixed few notations. Let's denote the identity element of G by this letter E, and the identity element of G prime by the letter E prime. Okay, and we denote the inverse of phi by this letter psi. Okay, note that this inverse makes sense as we have already discussed, and I think we have solved it in some of the exercises in the problem sets, that that if you have an isomorphism, I mean a group homomorphism phi from G to G prime is an isomorphism if and only if it is bijective. Okay, and once you have a bijective function, sorry, then you can talk about its inverse, and inverse of a group isomorphism is also a group homomorphism, and more generally it's a group isomorphism. Okay, so the inverse of phi that we are talking about here, that is a bijective function from G prime to G, and there is also a group isomorphism. Okay, in particular this is a group homomorphism, the psi. Okay, sorry. So now let's start with an element little g from G and assume that this is a finite order, okay? And note that if we have G power n is E, okay, then it is automatic that phi g raised to n will be E prime, okay? The reason is that, at least naively speaking, the reason is that a group homomorphism respects the structure of the group. I mean, it respects the group law, okay, precisely for that reason. And to compute G power n, you care for the group law. That was a naive argument, okay, and we need to have a precise version of that argument, and the precise version is here. So we look at phi g raised to n, that turns out to be phi of g raised to n, because this equality holds because phi is a group homomorphism, okay, and we know that G power n is the identity, and phi being a homomorphism sends the identity element to the identity element of the target group, okay. So this proves that phi g also has got finite order, and its order divides n, okay. So this order of phi g divides the order of G. And on the other hand, if you use a similar argument, it follows that okay, so let's just try to revisit. So we have we have a homomorphism phi from G to G prime, and we have picked an element G, and its image is of course phi of G. We know that the order of phi G divides the order of G, right? Yeah, and let's try to, okay, there is not much space though, but still let me do it here because it shouldn't. So now we consider the map psi from G prime to G. I mean, this group homomorphism psi from G prime to G. By the same argument, we know that the order of an, so here we have proved that the order of G, that is the order of the element that you have started with, is that is a multiple of the order of its image, okay. So by the same token, we know that okay, so we can replace G by phi of G here, okay. So note that phi G is an element of G prime, and if we apply psi, then we get psi of phi of G, okay. So you know, so it follows that the order of the, we start with the element phi of G, okay. So the order of phi G, that is divisible by the order of its image under psi, okay. In other words, the order of psi of G divides the order of phi G, okay, and psi of G is just G. So we have proved that the order of G divides the order of phi G. So there are two statements that we have proved so far, that the order of phi G divides the order of G, and that the order of G divides the order of phi G, okay. So it follows that the order of G and the order of phi G, they are equal, right? So we are done only in the case when the chosen element G has got finite order, okay. So another case that you need to consider is that when the order of G is infinite, okay, then the order of phi G also has to be infinite. If it were not the case, in other words, if the order of phi G were finite, then again, using a similar argument, it follows that order of its image has to be finite. The point is that if G has got finite order, then by this argument we see that phi G has to have finite order. So if G has finite order, then phi G has to have finite order, right? So this is what we have already proved, right? So the image of, a finite, so a group homomorphism sends a finite order element to a finite order element, right? Yeah, and if the order of phi G were finite, then psi would send it to a finite order element, but psi sends phi G to G in that. So G has to be an element of finite order, which is a contradiction to the hypothesis that you have started with, okay. So the order of phi G has to be infinite, okay. And again, this concludes, thus this concludes this statement in the case when G has got infinite order. We have already dealt with the situation when G has got finite order, so we are done, okay. So now regarding this deduction, so where you have to show that the number of elements of G of order D is equal to the number of elements of G prime of order D. You can rather provide exhibit a bijection from one set to the other. More precisely, if you look at the set of elements of G of order D and denote it by XD, and if you look at the set of all elements of G prime of order D and denoted by X prime D, okay, then one can exhibit a bijection from XD to X prime D. Okay, this bijection can be obtained by this isomorphism phi that we have started with, that we have been given. Okay, we know that I mean, if we say if we know that if we take an element of XD, that is, if we pick an element of G of order D, okay, then under the map phi it goes to an element of G prime of order D. So if you look at the restriction of the map phi to the subset XD, to the subset XD of the group G, then this restriction map takes XD to XD prime, right? The restriction of the map phi to the subset XD, sorry, the image of the restriction of, let me write it down. Oh no. By part 1, the image of the restriction of the map phi to the subset XD of G is contained in XD prime, and that shows that this is well defined. Okay. Yeah, that shows that this map phi restricted to XZ when the target space is XZ prime, then this map is well defined. Okay. Now similarly we can again apply all this argument to the map psi from G prime to G, okay, and that provides us a map from XG prime to XZ. Okay, and now since the compositions of both the maps are identities, okay, on the respective groups, it follows that this restriction maps, their composition also become identity on the respective domains. Okay, and then this follows that the map any of these two maps, and in fact both the maps, they are bijections. Okay, so it automatically follows that the number of elements of G of order D is equal to the number of elements of G prime of order D. Okay, fine. Yeah, so we have already been learning a while. I mean, it has been a while that we have been learning certain how to say, certain general notions related to groups. Okay, and it has been a couple of weeks that we haven't seen an explicit example of a group. Okay, so let's try to learn this example of quaternion group. I'm not so sure. I think I have introduced it, but I'm not so sure about it. So let's just discuss it. Okay, maybe I have introduced in the problem set, but maybe not in the lecture notes. Okay, but anyway, or maybe I just introduced it without even introducing the name. Okay, so if we look at these matrices, note that there are 8 matrices. So we're just taking few 2 by 2 matrices. All of them are invertible. Okay, so by plus minus this matrix, I mean you take this and the negative of that, and then you take this matrix and the negative of that, then you take this matrix and the negative of it, and then you take this matrix and it's negative. So altogether you have got 8 elements. Okay, I mean 8 distinct elements that you can really see. Okay, so for example, I mean these two matrices, they are distinct up to signs. These two matrices won't match up to signs because diagonally we have got reals and complex numbers here, and this doesn't match with this because this is the entries along the diagonal, the non-zero entries, and it has got non-zero entries along the, how do you call this, off diagonal, and this matrix can't be equal to this matrix up to signs. Okay, for the same reasoning and so on. So you can check that if you look at this if you consider this matrix, this one and this one and this one, and its negatives, you end up getting 8 distinct elements. Okay, and this example slash exercise says that this is a group under matrix multiplication, and this is known as the group of quaternions. Okay, so this is a group of order 8, right? So maybe one can try to relate this group with some dihedral group. One can try to relate and see what happens. We already know that this dihedral group D2n, we already know that D2n has got D2n, we know that this has got order n, right? So maybe if you look at D8, one can ask, is it true that quaternion group, this Q8 is isomorphic to D8. Okay, or are these two groups related, at least in some sense? As of now, you know this notion of isomorphism to relate them. We'll see. We'll come to this question. Yeah, we have already, regarding these dihedral groups, we have already counted its number of elements of order 2 in one of the problems in the previous problem set. I think in exercise 11, right? I think in problem set 6, right? Mm, yeah. Inside this dihedral group D2n, there are n, how to say, usual elements of order 8, namely the multiples of the reflection S. By multiple, I mean you look at the element S, SR square till SR power n minus 1. They are all elements of order n. Just give me a moment. Oh yeah, sorry, they are all elements of order 2. Sorry for the mess. So S, SR and all the way till SR power n minus 1, they are all elements of order 2. And in addition to these n elements, you end up getting another element, some power of r. Okay, depending on the parity of n. If n is even, then you look at r to the power n by 2. This is an element of order 2. And if n is odd, then the subgroup generated by r contains no elements of order 2. Okay. So thus, if n is even, you end up getting n and along with one more element, right? This 1 plus minus 1 raised to n, which is 1. 1 plus minus 1 raised to n over 2, which is 1 when n is even, right? So you end up getting these many elements of order 2, okay? And when n is odd, you just end up getting exactly n elements of order 2. And we have also seen that this is precisely the number of subgroups of order 2, okay? So the number of elements of order 2 and the number of subgroups of order 2 for this dihedral group D2n, they coincide, and this is not a this is not something specific to this dihedral group D2n. It holds in generality. Okay, so here we have a more general result. Okay, this says that if we have a group G, then the subgroups of G of order 2, they're in a one-to-one correspondence with the elements of G of order 2. Okay, and as you'd expect, or maybe you'd imagine, and as you already knew in the previous situation, that if you pick an element from the dihedral group of order 2, maybe S, okay, sorry, I did not even pick, I directly picked such a subgroup. If you pick this element S of order 2, then you can look at 1 comma S. That is a subgroup of dihedral group D2n of order 2. For example, if you end up taking SR square, then this subgroup generated by S square, okay, that is a subgroup of the dihedral group of order 2, okay. There's a subgroup of order 2. There is a subgroup containing the dihedral group, and the subgroup has got order 2. I do not mean that the dihedral group has got order 2. Okay, anyway, so the same strategy works, okay, in more general situation also. So you start with an element X and send it to the subgroup generated by X. Of course, that has to be, you start with an element of order 2 and send it to send it to the subgroup of G generated by that element X of order 2. So you have to collect all the integral powers of X, and you will see that among all the integral powers of X, there are only two distinct powers. So namely X power 0 or X square. All even powers of X, which includes X squared, X to the power 2, X to the power minus 2, X to the power minus 4, X to the power 4. All of them are equal to 1. Okay. So I was just somewhat carried away. I just got somewhat carried away with the notations that you were supposed to use, or that you decided to use in the context of dihedral groups. So let me indicate that. We'll use E here, not 1. Okay. Okay. Yeah. Or maybe just let me just give me a moment. Let me make this a bit clear. So let me put a cross here so that you can see what I'm cancelling out. So you put an E, the identity element. Okay. Yeah. So we look at the subgroup of G generated by the element X. So that consists of exactly two distinct elements, namely the identity element and the element X. Okay. So this is a map from the set of all order 2 elements of G to the set of all subgroups of G of order 2. Okay. And it sends an order 2 element X of G to the subgroup of G generated by X. Okay. And we claim that this map provides such a one-to-one correspondence. In fact, if we pick an element X of order 2, let's first note that the subgroup of G generated by X is indeed of order 2, and thus this above map from this set of all elements of G of order 2 to the set of all subgroups of G of order 2, that is a well-defined map. Okay. Okay, that's the first thing that you need to see. Hmm. Whoops. Yeah, so this shows that this map is well defined. I did not specifically write or add this word well defined. So this shows that the above map is well defined, and it also shows that, I mean, one can immediately say this above map is injective. Indeed, I mean, if you take two elements x and y, okay, and send it to the subgroup generated by, uh, I mean, okay, very roughly speaking, the point is that the x that you start with can be recovered from the subgroup generated by x. How? So this x is a unique non-trivial element of the subgroup of G generated by the element x. More precisely, if you start with two elements x and y, okay, which belong to this set, and then if you look at the subgroup, oops, if you look at the subgroup generated by x and the subgroup generated by y, and if you say that these two are equal, then you are saying, sorry, you're saying that ex is equal to e comma y, and comparing the non-trivial elements, you get x equal to y. So the injectivity is clear. And now for the surjectivity, we start with a subgroup H of G of order 2, and it follows that H is equal to the image of its non-trivial element under the above map, right? So yeah, as you see, and I mean, you might be under the impression that this is no different from what we have been discussing in the context of dihedral groups. Yeah, for sure. I mean, there is no how do you say, this argument is not genuinely different from what we already knew, or at least in some implicit form what you already knew in the context of dihedral groups. But the point is that sometimes working explicitly with certain groups may lead us to some result which holds in greater generality. Okay, so that's why I introduced this exercise at this point of time. Okay, after learning this results about the dihedral groups. Okay, great. So this map, as we have defined above, this provides us one desired one-to-one correspondence. Okay, between the subgroups of G of order 2 and the elements of G of order 2. Okay, so now as I was discussing that we already have this quaternion group. This is a group of ordered 8, and on the other hand we have this group D24, right? I mean D2n with n equal to 4, which is D8. So can we expect that this quaternion group, or can we prove or expect or prove or disprove that this quaternion group Q8 is isomorphic to the dihedral group D8 of order 8? Okay, in fact it is not. There are several ways to see. Okay, and one such way would be to apply this proposition. Okay, this proposition says that I mean, the first part says that an isomorphism sends an element of order, I mean, for any integer n, it sends an element of order n to an element of order n, and an isomorphism also provides us a bijection between the number of elements of G of order d, between the number of, I mean, provides bijection between the set of elements of G of order d and the set of elements of G prime of order d, and in particular the number of elements of G of order d is equal to the number of elements of G prime of order d. Well, so let's try to see what can we get from the dihedral groups and from the quaternion group. So this exercise says that I have to prove that the quaternion group is not isomorphic to the dihedral group of order 8, and certainly it cannot be isomorphic to any other dihedral group, because an isomorphism preserves the order, because an isomorphism is a bijection, right? So it preserves the order of the groups, I mean, that is the sizes of the groups, right? Okay, so let's assume that let's assume on the contrary that there exists a group isomorphism. Okay, and then let's count the elements of order 2 inside the dihedral group D8. Okay, we know that the dihedral group D8 contains at least 4 elements of order 2, namely S, SR, SR square, SR cube. I mean, these are the quote-unquote easiest elements of order 2 to start with. By easiest, I mean this works for any dihedral group, right? And the power of R, okay, R is to n by 2, that works when n is even. Okay. And yeah, okay, so this dihedral group D8 happens to have several elements. By that I mean at least 4 elements of order 2. Okay, and the images of these elements under this phi, they has to be elements of Q8 of order 2. Okay, by the previous proposition, the proposition that we have discussed at the very beginning today. And now one can observe that inside the quaternion group Q8, this is the only element of order 2. Okay, so then not much can be done, in the sense that we obtain a contradiction. So inside the dihedral group D8, the number of elements of order 2 is at least 4. In fact, it is 5, as you know. On the other hand, inside Q8, if you compute the orders of these elements, okay, then you can see that only this element has got order equal to 2. So this contradicts the assumption, okay, because this leads us to a contradiction when you apply the first proposition, the proposition that you discussed, okay. The number of elements of order D has to be equal to the number of elements of G prime of order D for any positive integer D. So that fails to hold for D equal to 2. For D equal to 2, the proposition fails to hold in this context. So we cannot assume that there exists a group isomorphism from G8 to Q8, okay. In other words, this proves that this quaternion group is not isomorphic to the dihedral group of order 8. Okay, yeah, and maybe here you can find an alternate solution. Okay, so if you look at the group, Q8, so this contains 6 elements of order 4. Okay, you can check that. So to do all that, you first maybe compute the orders of all the elements of Q8. Okay, one can check that Q8 contains 6 elements of order 4. Okay, and so if the groups Q8 and D8 were isomorphic, then then this dihedral group would have 6 elements of order 4. If you look at so yeah, so on the other hand, if you look at 1 r square and r cube, so this you just get 4 elements from there, okay, and to get 6 elements of order 4, so among these 4 elements there has to be at least 2 elements of order 4. Okay, one can also say that among 1 r square and r cube, these two elements, this r and r cube, they are elements of order 4, and this doesn't have order 4, so all these elements has to have order 4. Or maybe you just say that we have to have 6 elements of order 4, and here you have already got 4 elements. Among them we should have at least 2 elements of order 4, but that is impossible because these are all elements of order 2. Okay, so it follows that Q8 and D8, they are not isomorphic. Okay, anyway, so through all these arguments, what I'm trying to point out is that if you are given two groups, okay, then usually there is no standard method. So there is no standard method to prove that they are isomorphic or to disprove that they are isomorphic. And even before you make an attempt to prove or disprove, okay, even before you make an attempt to prove that they are isomorphic, or you make an attempt to prove that they are non-isomorphic, there is no standard method to even come to a conclusion, or even there is no standard method to make a guess whether they're isomorphic or not isomorphic. Okay, so you have to just try all sort of methods that comes to that you are already aware of. You have to apply all sort of ideas that you may have. So for instance, you can try to apply this proposition, okay, in several manners. Okay, so for example, you can try to count the number of elements of order D in one group, and the number of elements of order D in the other group for several integers D. If you, for example, you could start with D equal to 1, well, then this is going to be the same, because the number of elements of G of order 1 is equal to 1, right? The identity element of a group is the only element of order 1. So this statement is valid for D equal to 1 for any two groups G and G prime. Now you start with maybe D equal to 2 and try to see what happens, okay, and then you move on, okay, and try to see what can be done. Okay, as I was discussing, that it's a good idea to determine the order of each element of QA, so please do it. Okay, so this, I'll just put it as an exercise. Okay, yeah, and here is an interesting statement or interesting exercise, is that an infinite cyclic group is isomorphic to the group of integers. Okay, so we have already discussed the notion of cyclic groups, and we have also studied certain infinite cyclic groups. Okay, but yeah, we have learned this notion of isomorphism just very recently, right, in last couple of lectures. So let's try to relate any infinite cyclic group to something that you already know. Okay, so maybe you can ask, why do we care for such exercises, or why do we care for such statements? The idea is that you have certain known set of groups, certain known bunch of examples, okay, certain bunch of groups that you're already familiar with. Okay, now if you end up seeing something that you are not familiar or you haven't seen before, then you first try to relate that new object, that new group with something that you already knew. For instance, if you could show, I mean, if you start with a group G that you, I mean, that you just met now, okay, and then if you could show that this group G is isomorphic to some at least one of the groups that you already knew, then you become more comfortable in the sense that I mean, an isomorphism says that these two groups are the same. I mean, their composition laws, uh, they behave in a compatible manner, right? So the group theoretic properties of G, I mean, if two groups G1 and G2 they are isomorphic, then the group theoretic properties of G1 and G2 they are the same. For instance, the number of subgroups of G1 is same as the number of subgroups of G2. If you look at the number of elements of G1 of order D for some integer D, then that is equal to the number of elements of G2, number of elements of G2 of order D, and so on. Okay, so if we have two isomorphic groups, then their group theoretic properties they are the same. Okay, so that's why whenever we get to meet a new group, we try to see whether it is already isomorphic to something that you already knew. For instance, here you just made this group this Q8. Okay, this is a group of order 8, and you try to see whether this is isomorphic to the diagonal group D8, and it turns out that it is not the case, as you just saw here. For example, you can also ask whether Q8 is isomorphic to Z mod 8Z. Okay, whether these two are isomorphic or not, whether Q8 is isomorphic to mu 8 or not. So you certainly know that if you could show that Q8 and Z mod 8Z they are not isomorphic, then it will follow immediately that Q8 and mu 8 they are not isomorphic, because if you know that Q8 is not isomorphic to Z mod 8Z, then Q8 cannot be isomorphic to mu 8, because if Q8 were isomorphic to mu 8, then you know that mu 8 is isomorphic to Z mod 8Z, and then by the transitivity that you proved in one of the exercises in the problem sets, it was also put in this lecture notes. Since you know that the notion of being isomorphic is a transitive relation, it would follow that Q8 is isomorphic to Z mod 8Z, but that is not the case, right? I mean, if you end up proving it. So you can try to think about this question. So determine whether Q8, sorry for this bad handwriting, whether Q8 is isomorphic to, oops, the diagonal group has already been discussed, whether this is isomorphic to Z mod 8Z. Okay, yeah. So now we can focus on this exercise, which says that any infinite cyclic group is isomorphic to the group of integers. Okay, so let's start with an infinite cyclic group G, capital G, generated by an element little g of it. Okay, so now we define a map phi from Z to G. Okay, this is an argument that you have seen over and over again in some form or the other. Okay, and this is one of the standard arguments. Okay, so we sent the integer n to G power n. Okay, for all n in Z, and then and then we first show that this phi is a group homomorphism. That is completely straightforward. We just go through it and you will immediately see, or rather I would suggest you to show that this map phi is a group homomorphism even before you take a look into this argument. Okay, and now we are going to show that this is an isomorphism. So first of all, it is clear that this is surjective, since capital G is generated by the element little g. Okay, and under this map you end up getting all the parts of the element little g. And to show that this is injective, again that is straightforward. Suppose an integer n goes to the identity element of G. Okay, so G power n is identity, okay, for some integer n. But well, that cannot be the case, because G is infinite and G is generated by G. So little g raised to no non-zero integer n can be the identity element of G. Okay, so G power n is 0 only when n equal to 0. Okay, and that establishes that this map phi, as we have just defined, that is a group isomorphism. Okay, great. Usually when we deal with set of all maybe isomorphisms, or maybe more generally set of all homomorphisms from a group G1 to G2, so suppose we are given two groups G1 and G2, okay, and we consider we're interested in the homomorphisms phi from G1 to G2. Then we look at the set of all homomorphisms. Sorry, just disappeared. So we look at all homomorphisms. We look at all, yeah, we look at all homomorphisms phi from G1 to G2, okay, and the set is denoted by Hom G1 G2. Uh, so Hom G1 G2, this Hom stands for homomorphism, okay. So we are looking at the set of all homomorphisms from G1 to G2, okay. So the set of all group homomorphisms from G1 to G2 is denoted by Hom G1 G2. This is just this set, okay. Okay, and here we have just discussed. Sorry. Yeah, so in the following exercise, we will discuss this set Hom ZG, okay, the set of all homomorphisms from Z to G, okay, and as you can maybe imagine that, see, Z is generated by only one element, okay, namely the integer 1. It's also generated by -1, but it's better to look at the element 1. At least you don't need to put the negative sign all the time. So we are going to determine, sorry, we are going to determine all the homomorphisms from Z to G. Okay, we have been learning this. I mean, we have learned this notion of homomorphism a while ago. So it's a good idea to determine all the homomorphisms, right? Okay, at least in certain specific instances. You've already seen this, some finite version of this. We have determined the homomorphisms from mu to G. It already disappeared. All homomorphisms from mu to G. This is something that we have done. Okay, this is the finite version, and let's now focus on the infinite version. Okay, and as you see, the argument is, I mean, completely straightforward. I mean, this is something that one would expect. So so the claim is that given an element little g of G, okay, we need to show that there exists, and the first claim is that for an element little g of G, there exists there exists a unique group homomorphism phi from Z to G such that phi of 1 is G. Okay, I mean, so you just do what you're supposed to do, because if you want phi of 1 to be G, then what is phi of 2? Okay, phi of 2 would be phi of 1 plus phi of 1, so that is phi of 1 composed with phi of 1, which is G square. More generally, if phi 1 is equal to G and if phi is a homomorphism, then phi of n has to be G power n. So you are forced to have this equality. So so you define this map phi from Z to G by the condition that you are forced to have. Okay, I mean, if at all, okay, see, this exercise says that prove that there exists a unique group homomorphism, blah blah blah. So let's forget this word unique. It says that there is a group homomorphism phi from Z to G satisfying this equality. Okay, so as of now we do not know, but this exercise says that it is the case. So note that if at all there is any such group homomorphism, okay, if at all there is any such group homomorphism, then this equality has to hold. So why don't you use that property to define homomorphism? Okay, we can't use the word homomorphism, we can use the word map as of now. So why don't you use that property to define a map first and then try to see whether there is a homomorphism or not. Okay, and you have already been through this argument, so you know that this is going to be a homomorphism. Okay, I'm just trying to share certain motivation or certain thoughts around all this. Okay, great. So you define phi of n to be G power n for any n in Z, and then it is straightforward to see that this phi is a group homomorphism. Okay, and now again, if you have a group homomorphism phi prime from maybe another group homomorphism phi prime from Z to G with phi prime of 1 equal to G, okay, and then then again one can show that phi prime applied to n has to be equal to G power n. Okay, well, yeah, so that we have discussed with all the details. Okay, with probably a bit too much amount of details, but it's a good idea. Okay, so let's go through that exercise. So we want to so this exercise says that there's a unique group homomorphism with this property. Okay, so let's try to see what is phi prime of 1. Okay, so we denote the composition law of G by this symbol star. Okay, and then let's try to see, because you're going to do certain computations, it's better to explicitly denote the composition law of the group G. Okay, so note that phi prime applied to 1 composed with phi prime applied to -1 composed with phi prime applied to 1 gives you the identity element of the group G. Okay, and that already shows that phi prime of -1 has to be the inverse of phi prime of 1. Well, that is always the case, because for any group homomorphism, maybe let me use psi. For any group homomorphism, we know psi of g raised to n is psi of g raised to minus n. So here we have minus 1, sorry, you have 1 raised to minus 1, which is the negative of 1 here. That will be the inverse of phi prime of 1. Okay, so we have assumed that phi prime is a group homomorphism with this property that phi prime of 1 is g. So phi prime of minus 1 is g inverse. Now it is straightforward to see that phi prime of n will be g power n for any non-zero for any non-zero integer n. For positive integer, it follows from this equality, and for negative integers, it follows from this information. Okay, for a positive integer n, phi prime of n is phi prime applied to 1 plus 1 plus 1 added n times, and one can show that this is g raised to n. And phi prime of minus n, when n is positive, one can show that this is minus 1 added with itself n times. I mean, phi prime evaluated at this sum, one can show that this is g raised to minus n. Okay, so in other words, we are proving that phi prime of m is equal to g raised to m for any integer m, and that proves that phi prime is equal to phi. This is what we were supposed to prove to show that there exists a unique group homomorphism satisfying this criterion. Okay, so there are kind of two statements which are hidden within this single one. The first statement is that there exists one group homomorphism, and other statement is that there exists a unique such group homomorphism. Okay, so to first show that there is indeed such a group homomorphism, by such I mean a group homomorphism satisfying this property, and then you need to show that if you have any group homomorphism that satisfies this condition that 1 goes to g under that group homomorphism, then that group homomorphism phi prime has to coincide with the group homomorphism phi. Okay, so it follows that there exists a unique group homomorphism phi from z to g with this condition that phi of 1 equal to g. Okay, great. So let's conclude here, and so please work on the exercises that we have here. Okay, on this quaternion groups and this dihedral groups. Okay, there are certain interesting exercises, and that will help you develop some intuition when you deal with groups in greater generality. Okay, let's conclude.